Hello, this is Yeli Shetty Priya Nagasai, e20cse188, eb11 from third year, and I am making a video on automata of CFG and CFL, which is also known as context-free grammar and context-free language. So, in automata theory, a formal language is a set of strings of symbols drawn from a finite alphabet. A formal language can be specified either by a set of rules that generate the language or by a formal machine that accepts or recognizes the language. Today, we will see the following. So, let's start. First, let us go through different kind of languages that are present in automata, as we already saw. So, the one that is in the middle, the one that is in the middle is called as regular grammar. Then the one above it is called as deterministic context-free language, which is then followed by context-free language. Then it is followed up by CSL, also known as context-sensitive languages. And above it, it's followed by recursive languages. And on the top, we have recursive enumerable languages. So, let me write down what they also mean. Regular language, then this is deterministic context-free language. This is just context-free language. Then this is context-sensitive language. This is recursive language, and the top one is known as recursive enumerable language. So let us briefly go through each of them. Regular grammar is accepted by something called as a finite automata, whereas deterministic context-free languages are accepted by deterministic push-down automata. A context-free language is then accepted by push-down automata, which is a generalized version. And then CSL is accepted by linear bound automata. Recursive language is accepted by halting Turing machine, and this is accepted by Turing machine. So as the circle shows, this is the circle for the languages present in Automata. If we draw a similar circle for the languages or the grammar that accepts these particular languages, is as following. So first we have regular grammar. On top of that we have deterministic context free grammar. Oh my bad. Regular grammar, then on that you have context free grammar, and on top of that you have context sensitive grammar, and on top of that you have unrestricted. So as we did it before, this is regular grammar, also known as type 3. This is context free grammar type 2. As you can guess, context sensitive grammar, also known as type 1, and this is unrestricted grammar, also known as type 0 grammar. So if you compare both of these, so yeah, it can be easily mapped that regular grammar is accepted by oh my bad, I've written the grammar here. Regular grammar. So yeah, this is accepted by this. Context free grammar can accept wait, I'll just do it in a different way. This can accept regular language. Context free grammar can accept context free language and deterministic context free language. This can accept context sensitive language, and unrestricted can accept recursive enumerable language and recursive languages. So yeah, these are the types of grammars. If you also want, we can make a table, we can make a chart for the same for different machines that accept different languages. So in the middle you have finite automata, on top of that you have DPDA, then PDA, then you have LBA, and then you have halting machine, and finally you have the Turing machine. So same strategy as before. This is finite automata. This is deterministic push down automata. This is just push down automata. Then this is linear bound automata. This is halting Turing machine, and finally we have the Turing machine. And now let's just make it clear that as we were discussing, PDA has two types. It has non-deterministic push-down automata and deterministic push-down automata. Turing machine also has non-deterministic and deterministic Turing machine. Same goes for finite automata, where you have NFA and DFA. Now, a lot of people get confused about which one is the more stronger one or which one has the more strength. So in Turing machine, these both have the same strength, same for NFA, but in a PDA, NPDA has more power than deterministic. And also I would like to clear something, that if you take a finite automata and you add the stack memory, you create push down automata. Now in push down automata, if you again add stack memory, you get Turing machine. So now, as of now, we have seen what is a language in automata, we have seen what is a grammar in automata. Now if you want to go in depth of what exactly is grammar, if that hasn't been clear for you, so grammar basically is defined by a quadruple which can be said as G contains V, T, P, and S. Now in these, what is V, what is T, what is P, and what is S? So let's find out what they all mean. V means a variable, T means a terminal, P means a production rule, and S means a start symbol. Cool. I know it doesn't make any sense as of now, so first let's see what exactly grammar means. Grammar is basically a standard way of representing a language, right? And you might ask, what exactly is a language? Language is basically a collection of strings. So now if we take for an example, let's take some regular grammar. Say you have S, let me make it bigger so that we can reiterate on it. So we have S, A, S, B. Cool. So now let's try to figure out what V, P, T, and S mean. So for that, this S in the beginning on the left side is called the start symbol, right? A and B are called terminals. This S here is your variable, which can be substituted, and production rule, as is written here, is basically your substitution rules. For substituting your variable. So now let us see how you can produce a language using grammar. Producing a language using grammar. So let's take an example as we did before. So let's again consider the same example, SASB, and let's also assume a random thing. So now if we consider this one, so as we said, this is our starting variable, this is our variable, this is our T1, T2, this side is our P1, and this is our P2, which is our production rule. So now based on that, if we have to write our language, the shortest language we can create is our epsilon. The next one, as the question suggests, it's ASB. Now what have we learned? That A and S are terminals, they cannot be changed, but our S can be substituted. So if we substitute this S with, say, lambda, right? So if we do that, we are left with A and B, right? So now let's move ahead. Now this is the solution. If we have substituted the S with epsilon, what if we substitute S with ASB again? So then you're left with ASB, and then B. I hope you understand that this one comes from S substitution. So if you then again substitute this particular S with epsilon or with ASB, you are again left with AABB, also known as A square B square, or again you're left with AA ASB BB, which again in here this is our substitution that we did. So again, if you convert this S into epsilon and ASB, we again get AAABBB, also known as A raised to 3 B raised to 3, and here you again get AAAA S B B B B, and this can go on forever and ever and ever. And I think we would come up with a situation where we can finally say that our language can be A raised to n B raised to n, right? Now what is the shortest our n can be? Here, if as you can see, the n is equal to 0, and then we keep increasing it, so the lesser value is a n greater than equal to 0. This is how we produce a language using the given grammar. This was just example 1. Let us see another example. Let's take it more complicated this time. So let us go with S produces SS, S produces ASB, S also produces BSA, and S produces epsilon. So for this, our language can be epsilon, it can be ASB, BSA, where we substitute. So for getting what I've done here, assume we have taken SS, where this S is where this S has been substituted by ASB and this substituted by BSA. And now if we assume that this S is being substituted by by epsilon each, we get another shortest one that we can assume as A, B, B, A. This language can also be written somewhat like where the language has equal number of A's and equal number of B's. So you might ask, what's the difference between this one and this one? In the first one, in the first question here, we had although these look a lot similar, they're not, because in this every A is followed by B, but here the language can be anything. Here only the length of A is equal to B, but they can be in any order. They can be like B B A A, A B B A, A B A B. It doesn't have a finite way of going ahead with this. Now let's come to the end of the video where we will be producing grammar using a certain language. So let me just get a good area for it. This might be the place for us. So here let us go from context-free language to context-free grammar. Now, like before we saw how to go from a grammar to language, now let us go from, say, let's just do what we did right now in a reverse manner. Here, if you see, the straightforward answer would be just to do ASB and lambda. To explain this, we have S, which can be substituted as lambda or ASB. So you get lambda and you get A, you get S and you get B. So now again we're left with a dilemma as to epsilon ASB. So now you're getting epsilon again and then you're getting ASB. So to get the output, you basically go from here and then you go A S B B and then you come up. So basically that's A B B if S is lambda. Cool. So this is our answer. Also, it's worth remembering that this means that A raised to n, B raised to n, where number of A's are followed by number of B's. It just makes it easier. But now that we know how it came, so even like you can somehow remember it. So let's now consider A raised to n, B raised to n by 2, where n again is by this. So for this, they're asking us to keep the minimum one. If you take n is equal to 0, so you get A raised to 0, B raised to 2, which is also BB. So our shortest string would be, so you need ASB, but then the shortest one is BB. So irrespective of anything, the smallest one you'll get is BB. For the third one, let's now assume A raised to 2n, B raised to n, such that n is less than or equal to 0. In this, again, if you take n is equal to 0, you'd get lambda. But if you take n is equal to 1, you're going to get AAB, right? So that's why our language will be AASB lambda, so that the shortest one is still lambda, but then you're also getting double. So now let's come to something more interesting, where you have something called as a palindrome. So in palindromes, basically you have it basically repeats. So for this, your grammar would be ASA or BSB. Now this one is a notation of even palindromes. Now of odd palindromes, you have W, A plus B, either A or B, and then you have the opposite of it. So for this one, your grammar would be ASA, BSB, A or B, and your shortest one can be still lambda. So just the last example before we wrap up. Let us take a raised to m, b raised to m, c raised to n such that m comma n is less than equal to 0. So let us assume, so in this they want us to figure out that a and b, let's take n is equal to 1. So and say let's n is equal to any random number. All they want us to do is to have same number of A's and same number of B's, and they don't really care how many number of C's are present. So for this, let us now first make a small grammar where you have A raised to, for this one, where they're equal. So that again is A S1B, as we've always made it. And you have lambda because it's the smallest one you can make, where m and n is equal to 0. But then the issue comes with C, where you're telling them that you would like to replace it with smaller c or lambda, because again n can be equal to 0. So then the final or the main string or the starting symbol would be S1C. So this is how you can make the language for it. Thank you so much for patiently listening to what I've been explaining. I really had fun trying to explain context-free grammar, context-free language. I hope you really understood.